In this video, we're going to talk about describing solution spaces. So as we mentioned in the past two videos, the reason that we care about the reduced row echelon form for an augmented matrix is it tells us exactly how to describe the solution set for a linear system. In the next few examples, we demonstrate how to describe the solution space directly from the reduced row echelon form. So here we have a matrix. This is in reduced row echelon form, and it corresponds to a system of three equations in four unknowns. We're going to label our four unknowns x1, x2, x3, and x4. The three rows of our matrix give us three equations. The first equation tells us that x1 plus 2x3 plus 3x4 is equal to 4. The second equation tells us x2 plus 5x3 plus 6x4 is equal to 7. And finally, our third equation is 0 equals 0. It's satisfied for any choice of x1, x2, x3, and x4. As a result, we can get rid of it. In the other two equations, we observe that the variables x3 and x4 appear. As a result, we're going to solve the first equation for x1 in terms of x3 and x4, and we'll solve the second equation for x2 in terms of x3 and x4. This gives us what we call the parametric description of our solution space. This is called a parametric description of our solution space because the two variables x3 and x4 parameterize the solutions. We call these two variables, x3 and x4, free variables. We call them free variables because you can choose any value that you like for x3 and any value that you like for x4. That is, we have 2 degrees of freedom here. The remaining two variables, x1 and x2, are called basic variables. These two variables, x1 and x2, depend on the choice of values for x3 and for x4. We can express this as a set of real numbers x1, x2, x3, x4, such that x1 is equal to 4 minus 2x3 minus 3x4, and x2 is equal to 7 minus 5x3 minus 6x4, or we can condense this even further, and we can see that our solution set naturally lies in R4, that is, four-dimensional real space. So as a remark, we observe that any time there is at least one free variable, the system has infinitely many solutions. For our next example, we're going to start with a system. We're going to use Gaussian elimination to find the reduced row echelon form of the augmented matrix, and then we'll interpret the solution space. So the first thing we do is we translate our system into an augmented matrix. Now that we have our augmented matrix, our first operation is to interchange row 1 with row 2. That way, the leading entry on the top row is a 1. Next, we'll use this leading entry to clear the entries below. We'll first subtract twice row 1 from row 2. Next, we'll add row 1 to row 3. Next, if we scale the second row by -1, the third row by 1/4, we'll have achieved row echelon form. Starting from the bottom up, we'll use our third row to clear the third column. Finally, to achieve reduced row echelon form, we'll use the second row to clear the second column. The reduced row echelon form here tells us that there is a unique solution, and it's given by the three equations, x equals -4, y equals -3, z equals 0, or simply the triple -4, -3, 0 in R3. For a final example, we want to describe the solution space to this system of 4 equations in 2 unknowns. It's a good idea to take a second, pause this video, and make an attempt at solving it yourself. Now that you've taken a second to give this a try on your own, let's work through the solution. First, we're going to translate this system into an augmented matrix. Now that we have an augmented matrix, since the leading entry in the first row is already a 1, we can use that 1 to clear the first column. We're going to first subtract row 1 from row 2. Next, we'll add row 1 to row 3. And then to finish clearing the first column, we'll add row 1 to row 4. Next, we'll scale both row 3 and row 4 by 1/2. We use row 3 to clear the entry below. Finally, we'll scale row 4 by -1, then use that fourth row to clear the third column. Now, we simply use the third row to clear the second column. And lastly, we rearrange so that the second row ends up on the bottom. Now we have our reduced row echelon form of our matrix. If we translate this back into 4 equations, we get x equals 0, y equals 0, and lastly, coming from the third row, 0 is equal to 1. The fact that this equation is always false tells us that this system does not have a solution. To understand why this system does not have a solution, let's go back to the original 4 equations. If we write down each of these 4 equations in a more familiar form, then we can think about this system geometrically. The first equation and the third equation give us 2 perpendicular lines with slope 1 and slope -1. The second equation gives us a line parallel to the first equation that passes through 0, 2. And our fourth equation gives us a line parallel to the third equation that passes through -2 on the y-axis. So we can see from the picture here that while some of these lines do intersect, there is no common point of intersection for all 4 of them. So this brings us to our final point for the video, and that is the notion of consistency. We say a system of linear equations is consistent if there exists at least one solution. Otherwise, we say the system is inconsistent. So far, we've encountered 3 types of systems: an inconsistent system and 2 types of consistent systems, those having one solution and those having infinitely many solutions. It turns out these are the only possibilities. So in the next video, we want to ask a natural question. Given a linear system, can we easily identify whether the system is consistent? If so, can we easily identify whether there is a unique solution?